Hey guys, welcome back to my channel. I hope all of you are doing fine. Uh, you know, with this corona thing going on, it must be really hard for many of you to pursue whatever you are actually doing, but do not lose hope yet. I think good days are pretty much near. Okay, let's be optimistic here. Okay, so today I am going to talk about Gaussian elimination and why it actually works. The most important thing is that why does it work, right? We have been told that okay, if you're given this set of linear equation, you can always just eliminate them and eliminate certain variables and put them into a upper triangular matrix and then just easily solve it or something similar to that, even if we're not told about this upper triangular thing, right? You probably have heard about row echelon form or probably RREF, right? Reduced row echelon form. But do you know why it actually works? What do I mean by it? Whether it works or not, right? What does it mean to that something is working? Okay, so it basically means that they should have the same set of solution, right? If after doing the whole Gaussian elimination process, if you find that the solution set is not same as the original set of equation, that it won't be good, right? Because we are trying to find the solution to our original set of equation, not to some reduced set of equations or something like that, right? Okay, so first of all, what is Gaussian elimination? Right, here we can do elementary row persons, only 3 of them are allowed. Okay, what are these? First of all, given any set of equations like these 3, we put them into this augmented matrix, right? So these coefficients are just put directly into the matrix, -3, 2, -1, and similarly you can see for the whole thing, right? I have just put in the coefficient, and what we are allowed to do is that to any row we can add a scalar multiple of any other row. Suppose to this row number 2 we are adding this twice r1, okay? So twice the this whatever row number 1 is that we're adding to row 2. Similarly, we are allowed to add row 1 to row 3 because it's just a scalar multiple of r1 and we are adding it to r3. So first operation, remember that we are allowed to add a row or any scalar multiple of it to another row, okay? That's allowed. Rule number 1. Rule number 2, we can swap 2 rows, okay? Suppose this is our first row, this is our third row, and we can swap them whenever we want to, okay? This can go to the top, this can come to the bottom. This is the second operation. Third operation, what we can do is that take any row and we can multiply it with any scalar, okay? That is also something which is allowed. Okay, now let's see why does it work. Okay, first of all, think about it. Okay, we have this particular set of equation, okay, and suppose it has got a solution. Suppose it has a solution set x, y, z, some solution, okay, alpha, beta, gamma, and if I take any linear combination of these equations, I am claiming that the same solution will be the solution of my new equation set. Okay, suppose I am multiplying it by 3 and okay, just let me just write it down so that you know exactly what is going on. Okay, suppose I have multiplied this by 2, multiplied this one by 1, and then add them. What we will get is that 6x plus 6x, 12x, similarly -8, -6, -14y, and there would be equation, right? A combination of these two. And again we are going to take multiple combination. Okay, suppose we multiply this one by 3 and then multiply this one by 7 and make a equation out of this. Similarly, we can make out the equation out of using all 3 of them. Okay, and I am claiming that whatever equation I make like this, okay, our original solution set will satisfy those equations as well. Why is the case? Because see, if you put the original solution set like alpha, beta, gamma to in the place of x, y, and z, this particular equation will be satisfied, right? And again, if you multiply it by any scalar, this is still satisfied. Okay, and if you add two things which are identity, then again we will get an identity. So any equation you make like this would be satisfied by the solution set to our original set of equations. Is that clear till now? So if it's not clear, what you can do is that you can try making up many equations from this particular equations that I have given you. And okay, for a hint, the solution of this particular set is 2, 2 and minus 1. Okay, so you can try making up many equations using these three equations by taking linear combinations of them, and see that whether this particular solution set is satisfying this. And I am claiming that yes, they are going to satisfy. So let me write this equation set to be A. Okay, so this is A. Suppose we are going to create another solution set, which let me call this equation to be P. Okay, let me just erase these things, they are not required anymore. Okay, P, Q and R, and I have a new equation set of equation. Okay, this is first equation is just 2P plus 3R. Okay, just the scalar multiplication of this equation plus 3 times this equation. Similarly, another equation is 5Q minus 2R, and many more like this. Okay, so I am claiming that the solution set of A, whatever the solution of A is, must be the solution of this particular set as well. So solution set, so it's a set of solutions. Okay, one, for example, one of them is 2 to minus 1, and there can be many solutions. Okay, for this particular case it is not, as you can see that the determinant is non-zero. Okay, for example, here if we find this determinant of this particular matrix, this would be just minus 12. Okay, this is an upper triangular matrix, right? Whenever you see a matrix like this, you can just multiply the diagonal elements. So this is just minus 3 times minus 2, which is 6 times minus 2, which is minus 12. As the determinant is not 0, we can take inverse of this whole matrix, right? And we can multiply it by this particular vector, and we will get unique solution. But even if it was not the case, then also even if we get infinite number of solution, then we will get a set of solutions, right? So that's what I am calling as solution set. Suppose the solution set of A is Sol A. Okay, Sol A. I am claiming that solution set of A is a subset of solution B, because it's pretty apparent, right? As I told you that anything that satisfied this set of equation that I am calling A must satisfy this set of equation, which are linear combination of these equations. Okay, similarly, if these equations are again linear combinations of these equations, I mean that any equation of system A is linear combination of equations from system B, then again another relation will satisfy, right? Solution A is a superset of solution B. So from these two, you pretty much understand that this solution set would be equal, right? Because it is both a subset and a superset. So from there, equality obviously follows. So now if we can see that in the row operations, okay, whatever we are allowed to do in Gaussian elimination, if we are just making linear combinations of the rows to make up a new set of equations, then we are conserving the solution sets, right, as we have described above. So here let's see, this equation is as it is here, right? This equation, whatever we had, now it is changed with a combination of this equation plus 2 times this equation. Okay, so this is again a linear combination of the above equation. Similarly, this equation is linear combination of this equation and this equation. Okay, so it's pretty clear that whatever the solution of this set is, that same solution, sorry, let me repeat. So whatever the solution of this set is, those solution will satisfy this system of equations as well, right? Okay, now the fun fact is that whatever we do in Gaussian elimination, those are reversible. Suppose we are allowed to multiply a row by a scalar. Okay, suppose I have multiplied this row by alpha. So to reverse this, we can do another multiplication by 1 by alpha. By that, we can just reverse this whole operation, right? Similarly, we are allowed to swap two rows. Again, that is reversible, isn't it? And adding a multiple of a particular row to a row is allowed. And the next time, if we add just the negative multiple of this previous row by the same constant or the same multiplier, then obviously we are cancelling out whatever we did. So it's pretty reversible. That way we can see that the solution should be conserved. So I guess you can pretty much see by now why Gaussian elimination should work, right? So that's what I wanted to explain in this particular video. I hope it's clear. If something is not clear, please reach out to me in the comment section. I'll try to clear it as soon as I can. And I hope you like the video, and that's all for the day. Thanks for watching.